Transformations, day 2, reflections. So a reflection is a transformation where each point of the original graph has an image point resulting from a reflection in a line. So we have two main reflections. We have a horizontal reflection and a vertical reflection. Pretty straightforward. Horizontal is a reflection of a graph in the y-axis. So I'm physically taking this point A and reflecting it like a mirror image along the or the y-axis to the other side. So this point -3, 5 would become, we'd call this A prime, +3, 5. So as a reflection in the y-axis, the x value changes from a positive to a negative or a negative to a positive, but the y value does not change. Vertical reflection does the exact opposite. It vertically reflects, so we're reflecting over the x-axis. So this point here at 4, 3 would become 4, -3. Okay, so in a vertical reflection or a reflection in the x-axis, the x value does not change, but the y value changes from a positive to the negative. So horizontal reflections affect the x. Vertical affect the y coordinates. Okay. So for example, given the following function, draw a new graph with a reflection in the x-axis. Well, if I'm reflecting this in the x-axis, it's a vertical reflection. So this A point actually isn't going to move because it's on the x-axis. So this is called, we'll talk about it next, the invariant point. Point B is going to reflect here. Point C is here. Point D is now down here. And point E is now down here. So if I were to quickly connect these, pretty straightforward. This would be my new graph of my reflection. This is C prime. Okay, across the y-axis, a little bit different. My A value is going to reflect here. My B value is to here. So there's my first line. My C value is not going to change because it's on the y-axis. My point D is going to reflect here. And my point E is going to reflect to here. So, new vocabulary. We've talked about this a little bit in grade 11. These are called, which is called an invariant point. It's a point on the graph that remains unchanged after a tried to it. What are the invariant points of each reflection above? Well, point A, the invariant point would be -3, 0, because that point did not change. So that was for the first one. For the second one, the invariant point would have been point B, which was at 0. Oh, sorry, not point B, but point C, because point C did not change, which is what 0, 2. So when we talk about reflections, a note to remember is that all invariant points will occur on the line of reflection. So a horizontal reflection, your invariant point is on the y-axis. A vertical, your invariant point is on the axis. Okay? Okay, this is just a quick demonstration on Desmo software. We're not going to go through it, but we'll just quickly describe what's happening. We started with and we described what's happening. If we apply this negative to the entire function, this is a reflection, reflects in the x-axis. Okay, if we apply a negative just to our x values and then apply brackets around those x values, this reflects in the y-axis. Okay, so same thing here, applying a negative to the entire function, we can kind of predict this reflects in x-axis, going to reflect in the y-axis. Okay, so given an original function, in summary, if you're given an original function and a negative is applied to the entire function, this is going to describe a vertical reflection, which reflects the graph in the x-axis. If a negative is applied just to your x coordinates, this describes a horizontal reflection, which reflects the graph in the y-axis. So, second example, the graph represented by the thin line is a reflection of the function represented by the thick line. Describe the transformation that must be applied, state the domain and range, and determine the invariant points. Determine its new equation. Okay, so pretty straightforward. Describe the transformation. Well, when I look at this, this has been reflected in the y-axis. The domain and range, well, the domain, it looks like, so we're looking at the graph represented by the thin line is, so the thin line is the reflection. So -5 to a +2. The range looks like it's from -1 to a +3. What is the invariant point? The invariant point is the point that does not change, and because we're reflecting in the y-axis, the point on the y-axis will be our invariant point. So this is our invariant point, which is at 0, -1/2. That's our invariant. And then write the new equation. Well, if it's a reflection in the y-axis, then that means it's a horizontal translation. That means all of our x values have changed from a positive to a negative. So I'm going to apply a negative just to my x coordinates. So it'd be y equals f of -x. B, again, same thing. It's a reflection in the y-axis. The domain, it looks like, is all real numbers. The range is anything greater than 0. The invariant point is on the y-axis again, which is at 0, 4. Our new equation. Okay, well, if we wrote this in equation notation now, because we have the equation, I want to apply a negative only to my x coordinates. So I'm going to write this as y equals absolute value of a -x plus 4. And that should create a horizontal reflection. All right. Your turn. Okay, so do your best. See if you can answer this next question. The key to this is on the website. Example 3 and 4, mapping notations for reflections. So giving the mapping notation, right, similar to before, if we start with a general point x, y, a negative x comma y is going to represent a horizontal reflection because we are switching the x coordinates to a negative. Same thing with vertical reflection. The mapping notation would be the y's being replaced with a negative, replacing the y value, which would mean a reflection in the x-axis. So example 3, describe how the graph of the second function compares to the graph of the first function. Well, if I look at this first equation, I'm starting with y equals 3 to the power of x. My second function, the x is being replaced with a negative x. So this tells me that there is going to be a reflection in the y-axis. All right, question B. I'm starting with a 2x plus 6, and then I'm left with a negative 2x minus 6. So this is a little tricky because what is kind of the difference between B and C here? Okay, this is tricky with like linear and quadratic equations because sometimes you don't really know if this negative is it being applied to the x or the entire function. Well, because I can factor out a negative out of this entire function, and I'm left with what the original function was, it tells me a negative has been applied to the entire function, which is a reflection in the x-axis. So vertical reflection, reflecting in the x-axis. Question C, if I factor out a negative out of this entire function, I will not be left with my original. So this tells me that this function was actually, the negative was actually just applied to the x, and then they just multiplied these values to get a negative 2x. So this tells me that there's a reflection in the y-axis, or horizontal. So little things to be aware of. Okay, example 4. The transform function of y equals g of x is y equals negative g of x. If the point A, negative 3 comma 5, lies on y equals g of x, what is the image point A prime of the transform function? Okay, so what does this tell us? Y equals negative g of x. This tells me there's a reflection in the x-axis, or you could call it a vertical reflection. Okay. So what does this affect? Well, technically a reflection in the x-axis is going to affect the y values. Therefore, point A is going to become the same. It's my y value that is going to be affected, which is going to be a negative 5. Okay, and that is reflections.